mutual inductance. These are the two coils are there, coil 1 and 2. Mutual inductance 0, non-zero. Just is asking only that much here. So let's assume current in the second coil. It will link the first coil. What about mutual inductance? Will be non-zero. Second case, how the plane of the coils? The plane of the coils are perpendicular. You can see this. The plane of coils are coils lie in same plane. Plane of coils are perpendicular. So what about mutual inductance? Will be zero. Now look at this. Coaxial. So mutual inductance must be non-zero. Already we have discussed. In this case, how the plane of the coils are no perpendicular. Mutual inductance will be zero. Now one more situation. If it is like this, if the coil is somewhere inclined, yes, of course it will be less than this value. It will be less than this value. Mutual inductance will be non-zero. Where you can look at the axis. They make some angle. Mutual will be non-zero. That one. Okay, later on one more is there, like even there'll be mutual inductance between two coils placed like this. That we'll discuss in the terrestrial magnetism. You please do remind, very important, because now I don't have any mathematics to show mutual inductance, but with the help of magnetism, very easily I can find out. Now the mathematics will not permit us to derive mutual inductance between two coils which are placed like this. If I use the bar magnet concept, very easy. Within 3-4 steps, I'll get it. So and I have kept reminder. You also please remind that one. Mutual inductance with bar magnet concept. It's a very good problem is there. Two coils with the mutual inductance. I'll give only the diagram. Proof I'll show in the magnetism chapter. These are the two coils are there. They lie in same plane. And look at their axis parallel. What about mutual inductance? Will be non-zero. So later in magnetism chapter, I'll give proof for that, because for that we need bar magnet concept. Okay, let's go for next one. No. First, without this cell, let me discuss the problem. So there's a resistance R1. There's a coil 2, which is having its resistance 2. So I'll call this as loop 1 or coil 1. This is a coil 2. I'm coming to the mutual inductance, the core idea. This one, till now what happened, we're just confining mutual inductance. Now self-inductance, mutual inductance. I'll introduce both. So these are the two loops are there. So there is no source of EMF for the coil 1, and there is only and a variable current I'll pass in the coil 2. Now because of the variable current, the flux generated by coil 2 will link coil 1. Will there be any EMF induced in this? Yes, it will be according to the formula. E1 should be equal to M di1 by dt. So what is the equivalent circuit diagram? I should show source of EMF. So according to this, how B bar will be out of the plane due to 2. Then negative flux, positive flux increases. d5 by dt, positive EMF induced, negative. So how the induced current should flow here? The induced current, should flow in clockwise here. Then there'll be also self-inductance of this coil, no? Self-inductance of also this coil 1 will come into picture. So then what is the total EMF induced? This should be equal to L di1 by dt plus M di2 by dt, because even a current I1 is flowing. Due to current flowing in this coil, will there be any EMF generated? S, and there'll be some self-inductance of this coil will be there. So what is the total EMF induced will be, I'll write like this: EMF induced in coil 1 should be equal to L1 di1 by dt plus M di2 by dt. This is due to what? EMF induced due to self-inductance. This is EMF induced due to mutual inductance. So both self-inductance as well as mutual inductance has to be taken care. So any current carrying structure will have self-inductance, keeping in mind. Now slowly we'll enter into the real application. Till now, we isolated ourselves, what happened? We separated ourselves, mutual self-inductance different here. So now what you have to do? You have to consider the effect of both self as well as mutual inductance will come into picture. Okay, next part of the thing. And now there is an external source, there is a cell. So I'll switch on the circuit. I'll switch on the circuit. What all can happen here now? This having self-inductance L1, this having L2, and mutual inductance, let it be M. If you want to write M1 to M21, again M12 equal to M1. Now both are RC circuits are there, no? So what will be the current in them? Will be variable, because we know current will decrease exponentially, both are variable. So a varying current flowing here will produce a magnetic field in the loop 1. A varying current I2 flowing in the loop 2 will produce a varying magnetic field in the loop 1. So flux link in the loop 1 will change. So therefore, what is the expression for overall equations? You can write it. Already the external cell is there. This is not EMF induced cell. So this I1 is due to what? Due to this one. So what is the okay, this magnitude I'm comparing. Only magnitudes I'm writing. If you only magnitudes I'm writing is that one. Now any equation can you write all together? Cell E1, then I1 should flow, then mutual inductance. Okay, okay. You want that negative sign? No? I'll introduce here. Yeah, fine. There should be source of EMF due to varying current, because this loop is having, so where is L1? L1 I need not to show it. The loop itself will have self-inductance. And because of two loops nearby, there'll be mutual inductance. Then what is the overall equation? E1 minus IR1 this minus L1 di1 by dt, mutual inductance M di2 by dt minus Q by C equal to 0, or charge in first capacitor Q1C equal to 0. This is what happens. From where this quantity has come? Due to self-inductance. What about this quantity? Due to mutual inductance. I'm trying to drag you to a concept where we need to think like this. This is due to, this EMF is due to mutual inductance. Clear now? Let's assume that there is no EMF. If there is no EMF, there is no cell 1. If there is no cell is there. In that case, I think this you eliminate. If there is no capacitor, this you eliminate. then what is the net EMF induced will be due to these two quantities. So therefore, we can never have only self-inductance, only mutual inductance. There must be both together. They are like a twin brothers, or like a say like a two sides of a coin. In for any circuit, self-inductance, mutual inductance will be present. Means, sir, like I'll remove this, then mutual inductance will vanish. Self-inductance must be there for any loop. Mutual inductance will come if any other loop comes. One or the other. See, practically what happen, like in a fan, there'll be coils, no? The adjacent coils or some other coils here and there, or some wire will come there. So there's a mutual inductance will be there practically. Intentionally, if you bring it or not, this will be present due to unwanted sources also. They may ask you any objective question like this. You should be able to write this equation. Got this? So here I took example of without cell. This what happened. The total EMF into the coil will be due to self-inductance due to this one. So here this is another situation. Okay, let's take help of this idea. Now I'll proceed to the inductors in series and parallel.